Hello, everyone. In this video, I will be going over the latent variable active partner interdependence model. So in previous videos, I've gone over kind of the baseline active partner interdependence model with observed variables, where we just take a sum or a mean score. But in this video, I'll be going over what does this model look like kind of in the latent space. And we'll also troubleshoot a couple of errors that we will see kind of along the way when using latent variables. So one of the benefits of using a latent variable model is that we can attenuate measurement error. Because when you are using sum scores, there's going to be actually quite a bit of measurement error that's going to attenuate your regression coefficients, either upwardly or downwardly, most often downwardly, but of course it can also upwardly bias your coefficients where they are actually stronger than they are in kind of actuality in the population. What latent variables allows us to do is to model that measurement error, and we can get unbiased estimates of our structural associations, our actor effects, and our partner effects. All right, so we'll jump in and we'll be using a data set that was collected with 305 heterosexual couples. And so we'll be using dyadic coping and relationship quality as our two variables within our actor partner interdependence model with latent variables. So we'll start here at the use variables line. We have our male items up here. So if they have an underscore M at the end, then they are male. And if they don't have that underscore M at the end, then they are female. And so relationship quality is measured with four items, and we are using the common dyadic coping subscale from the dyadic coping inventory. And so we just specify all of these variables that are going to be in our model. We have our missing command. We have relatively little missing data, but we do need to enter it in and tell Mplus we have some missing data and that all variables with a 999 in that cell, that means that the data is missing. Because if you do not specify this and you have a negative 999 value, Mplus will think it's a legitimate value and it will severely skew your results and you will get some very odd results. So that's a common coding error that I see and I often continue to make is not specifying my missing data. Right. We also have an ID variable that won't be as pertinent to what we are doing here, but I always have an ID variable because what it allows us to do is look at plots. But I am on a Mac, and unfortunately, Mplus does not allow for kind of data visualization if you are using a Mac. But if you do have a Windows computer, then this will be more relevant where you can look at outliers and things like that. Right. So in Mplus, the default is maximum likelihood, but relationship quality tends to be, skewed and also kurtotic. And so one of the ways we try to address that, rather than using a nonlinear transformation like a log transformation, is to go in on the back end and adjust the standard errors and our chi-square values by using robust maximum likelihood. All right, so moving into our model command, the first thing that we are going to do is we are going to specify our four latent variables. So we have first relationship quality measured by the couple satisfaction index, specified by those four items. And you will also notice that I am using the second item first, because by default, what Mplus does is that first item following this by statement is automatically fixed to one. This is what's called the marker method. And again, this is going to be the default in most all statistical programs. I know it is in Lavon, Mplus, and I'm sure in other SEM softwares like SAS and OpenMX and these other programs out there. And so the reason I did this is because Item one is actually non-invariant. So what that means is that the factor loading or the regression coefficient between the latent variable and the actual item isn't the same across males and females. And so what that does is in the marker method, that first indicator kind of sets the scale. So latent variables don't have a mean, they don't have a variance because they are latent, they are unobserved. And so we need to give them a mean and we need to give them a variance. And through the marker method, we do that through fixing that first factor loading to 1 and that first intercept to 0. But if you have an item that doesn't operate the same way across men and women, you're actually setting the scale for the latent variables, and they're going to be on different metrics for men and women. So let's say, for example, your first factor loading for men is 0.90 and for women it's 0.70. So even though you're using the same item, that item is performing differently in men and women. And so the variance of your latent variable is then going to be skewed and biased across men and women, which means we actually cannot compare the regression coefficients, the actor and partner effects. So we couldn't constrain those actor effects to be equal, and we couldn't constrain those partner effects to be equal if that first item is non-invariant. All right. And so again, that's going to be a critical piece of effective, modeling in general, but also in dyadic data. And it also tells us that we need to be testing measurement invariance in all of our dyadic studies, right, across men and women, because we might be modeling more measurement error more so than anything else. All right, so I'll save any further discussion more for, a measurement invariance video, or there's again tons of resources out there around confirmatory factor analysis, and there's even more coming out. There was a 2021 article on dyadic measurement invariance that talks a lot about some of the implications of non-invariance. So there's plenty of resources out there for you all. But I at least want to talk a little bit about why I'm doing something that might seem a little weird, right? And so essentially, what we have is partial invariance here. We have everything else. CSI 2, 3, and 4 are the exact same. Those factor loadings are exact same across men and women. But again, this first one is not, which means we have partial invariance, right? And then we also have our male dyadic coping latent variable and our female dyadic coping latent variable. And then we move on to the structural portion of our model. And so we have relationship quality by men and women being predicted by dyadic coping for men. So this will be an actor effect here. And then this will be a partner. And then this will be a partner. And then this will be an actor. So it's an actor effect because it's male CSI being predicted by male dyadic coping. And it's a partner effect here because it's women's relationship quality being predicted by male dyadic coping. And you have the same thing down here. All right, next, in dyadic data, when we are using latent variables, we want to correlate those residuals. So what that means is dyadic coping for women, that first item is going to correlate with that first item of dyadic coping for men. So because there might be a common cause or a common influence on why or how men and women respond similarly or perhaps differently to that item. And we want to account for that in our model. Because what can happen if we don't do this is that the covariance between the latent variables is actually going to be biased, either upwardly or downwardly, depending on that correlation, and that can actually have ripple effects down to other parts of your model, such as the actor and partner effects. So that's going to be exceptionally important that you correlate the residuals for all of the items. Likewise, we are doing that for the relationship quality variable, where the second item is correlated with the second item across gender as our distinguishing variable in this model. And then the last thing we'll do is we will actually have to enter in those covariances between the latent factors. All right, so we want to covary male relationship quality with female relationship quality. It is not sufficient just to correlate the residuals. You also have to correlate the latent constructs with each other. All right, so we will do that real quick. And then down here, I'll actually get rid of this since we can't do plotting since I'm on a Mac. Um, what we can do now is we can run this, and we're actually going to find that the model fits okay, but there's something we're actually we have to do a little bit of investigative work to see what might actually be happening because we're going to run into an error or two. Right? So we'll scroll down. Um, And the primary message that we want to look at is that the model terminated normally. So that's really good. So it means we didn't get any error messages like a non-positive definite matrix. Our model converged. So we are good to go with providing an initial interpretation of what is going on in our data. All right, so we have our chi-square fit. When using structural equation modeling, particularly when you are using lots of latent variables, this is almost always significant. If you can use only latent variables and you get a non-significant chi-square, then more power to you. I don't think I've ever seen that before. Or if I have, it's exceptionally rare because that chi-square statistic is really, really sensitive to even minor misspecifications. So this is just one piece of information that we will use in evaluating model data fit. We have our RMSCA. It's okay. It's really nothing to brag about. Our 90% confidence interval is actually pretty tight, which is actually a good sign. But it's again, this is higher than we would really want it. It's certainly well within established cutoffs, whether you're a 0.05 person, a 0.06 person, or perhaps a 0.08 person. Generally, this is going to be in within the realm of possibility of it being a good fitting model. And our high end on their 90% confidence interval isn't above 0.08, which again, it lends a little bit more credence to we have a decent fitting model here. Our CFI and our TLI are not great. They are below the 0.95 recommendations proposed by Hu and Bentler. Our model is actually fairly similar to what they did. We just have an additional set of latent variables. They originally created their cutoffs that are exceptionally overgeneralized based on a two-factor confirmatory factor analysis. So we're kind of close, but again, that there is something that we'll want to kind of poke around on, and we'll want to begin to think about. All right, so we can scroll down and we can look at our standardized estimates first, or unstandardized, I should say. Scroll down to our standardized. So here is our non-invariant loading that I had talked about previously. We have 0.56 for men, and we have 0.68 for women. So again, if we had had that as our scaling variable, then our variances down here, I guess I should probably scroll up to the unstandardized, would actually be quite a bit different. And again, it would preclude accurate conclusions when comparing men and women. All right, so everything looks fine here. We have good factor loadings. There are some that are a little lower than we would want them. Down here, 0.56, 0.63. We generally want them to be above 0.70. But generally, we have some good loadings. At this point, I'm not really, here's our actor and partner effects. I'm not really interested in interpreting them at this point, simply because we don't have a great model data fit. A lot of people might kind of stop here, but I'm going to kind of poke around to see what might actually be happening, what might actually be going on in the model. And so my preference is to use the residual matrix, which is the expected subtracted by the model implied covariance matrix. And you do that, I'll scroll up to my syntax in the output by typing in residual. And so this will give you a covariance difference between what is expected and what is actually found. It will give you a correlation difference. So you standardize that covariance and it's in a metric that we can kind of understand. And it also give you a z-score associated with that. Right? So this is kind of what's called local misfit. All right, so in generally this will be labeled by your residual output. And so we're not going to look at means, all right, because the mean part of our model is actually saturated when we haven't fixed any of the item intercepts or the latent means to be any specific value or fix them to be zero. So we can ignore the mean structure. It is saturated. All right. So first we have our model estimated covariances, and then we have model estimated correlations. And then we have the residuals, which is the difference. And then we can scroll down and we have the residuals for the correlations, right? And then if we scroll down even further, then we have our z-scores, right? So how you interpret this is that a negative value means it's underestimated, right? And if you remember back to kind of Stat 101, your z-score, your critical value is 1.96. So that means technically any value above 1.96 indicates that there's some over or underestimation, right? So again, negative is over or under, excuse me, and then positive is actually overestimation. So in this example, the first item for men and the fourth item for, I believe this is also men, um, the underscore M went away. So you can just type that in, is overestimated, right? Based on what the model had expected. And so you can take a really stringent approach where every value above 1.96, either positive or negative, should be addressed. I take more of a kind of a gestalt approach because again, these estimates are going to be actually fairly sensitive to sample size and things like that. So I'm not all that kind of rigid with them, where if it's above 1.96, that means I have a bad fitting model. Um, I kind of look for kind of trends. I look for themes. You know, for example, is one item constantly over or underestimated? Um, is there an outlying value? So like you see most of them are, you know, between kind of 1.5 and negative 1.5. But we have, you know, one here that's 3.5. So that one's a little sticks out a little bit. Um, so these are the things I kind of look for when looking at the residual matrix. And I also consult the actual correlations too, because again, you know, we'll take a look in CSI 1M and dyadic coping 5M. That's, you know, 3.5. That's kind of 3 times bigger than the kind of, I would say, eyeballing it, kind of average of all of the other residuals. So it's telling us that there's something going on here, but we want to scroll up and kind of go to that same association. And it looks like, according to the model, that the correlation between these two is being overestimated by 0.14, which is really quite substantial, right? So let's say our model expected a correlation of 0.50, just picking out a random number. What the model actually found was a correlation of 0.64. And just thinking about what a correlation represents, that could be fairly substantial, right? And if you square this value, then you get the amount of variance that is overestimated. And so I think 14 times 14 is 196. Um, and so it could be like, you know, something like 9% of the variance, or pardon my bad mental math, but somewhere in there, it could be, you know, fairly substantial. All right. So we need to potentially address that. All right. So we'll we've taken note of this one. It's kind of a little bit higher. You know, this one's kind of getting there a little bit. Um, Kind of this one's a little higher too. We got a 5 here. That's definitely that's potentially problematic. And as you'll see, for some of these diagonal elements like this one, that's the variance, right? So all of these are covariances or correlations. Those on the diagonal are actually the variances, right? So this one's really quite concerning. Uh, Here we got this one too, CSI 1 and 4. It's underestimated. And we got a big honkin' one down here, actually a couple, with dyadic coping 5. So I'm sensing a theme here of dyadic coping 5 isn't behaving all that well, right? So it's got two honkin' values right here. It's got another one right here. Um, it seems to be kind of not behaving all that well. And you can see here, -2, -2, -2, -2. There's something going on here with this item. All right. And so there's a bunch of things that we could do here. We could, potentially investigate a residual correlation. We could just simply drop the item. There are perhaps there's an omitted cross-loading somewhere. There's again a lot of different possibilities. All right. So one of the things that we can do is take a data-driven approach and just throw everything at it and kind of see what happens. That's probably not the best approach. And so what we can actually do is actually go back and look at the items. And so these are the five items that we are kind of looking at this in our model, and it's this one. All right. So this is the one that is kind of not behaving. And so I'm looking at the first three items. So we try to cope with our problems. So that's about stress communication. We talk about our problems. Again, that's stress communication. We reframe the problem, put it into perspective. That's stress communication. And then we move into here. It's like we kind of distract ourselves, or perhaps this is how we recharge from stress. This isn't stress communication, really. We are affectionate towards each other. Again, this is kind of the same thing where it's not really about stress communication. And if you recall, I set the scale of the latent variable with this one. So you can kind of theoretically think about it as how I'm defining dyadic coping statistically is really about stress communication between the dyad members, between the male-female dyads, our partners. And so these three items are doing a really nice job. These items are not really getting at what we're really kind of wanting, or how we're statistically modeling our theory. And so if we scroll up, we can go back to our standardized output, and we kind of see that. Like these loadings are actually quite a bit lower by 0.10 than the others. And that's true for male, and that's also, true for female. So we have a couple of options here now that we've identified a potential area that's problematic. We'll do one thing first, and we'll kind of see how it goes. Let's correlate the residuals of dyadic coping 4 and 5. All right. So we're going to do that only within a dyad member. So I'm only going to correlate men with men and women with women. All right. And we're going to just see how that works. All right. So that needs to be a 5. This needs to be actually that needs to be that. So this will be the male covariance, and then this will be the female covariance. All right, and then we can re-estimate our model. All right. And so here, I'm not going to kind of walk you through the kind of the formal steps of a likelihood ratio test. But what you would do here is you'd actually run a chi-square difference test to see if adding these two parameters significantly increases the fit of the model. But we can see our RMSEA went down by almost 16%. It went from 0.60 to 0.51. Our CFI was like 0.946, somewhere in there. And our TLI was like 928 or something like that. So we're moving in the right direction. All right. And so we can just take a quick glance at the factor loadings. You'll see that uh, item 4 actually went down. This factor loading went down by adding in that covariance. Same thing over here. All right. So this tells us that there was some bias going on. Again, assuming that this is the population model, some bias going on in the factor loading of item 4. All right. So we'll kind of scroll down and we'll look at that residual matrix again. All right, so we'll look at the z-scores, um, kind of scanning everywhere. Here we still have, those two kind of larger problems in terms of those covariances, but that's probably fairly understandable, right? Because we're not really tinkering around in this area of the model. We're really just tinkering around here. So that means that there's very few ripples or very few waves that are happening, messing around here, moving all the way to the item level of our dependent variable. So we'll keep scrolling down. We'll keep scrolling down, and we can see here that um, that our z-scores went down substantially. Here, this is actually so small you can't estimate. So this is not necessarily a problem. And this was, I forgot, maybe it was somewhere around 5 or 6 before, and now it's 1.24, which is kind of well within our 1.96 kind of cutoff. Right. So this substantially improved our model in a variety of different ways, including our residual matrix as well as our kind of global fit statistics. All right. But here, what we have is some more problems, right? So we have, it's really these four, these and these. So this means that, 4 and 5 for men and 4 and 5 for women are still being overestimated. So it actually kind of does make a little bit of theoretical sense to correlate men's item 5 with women's item 4, right? So we'll do this, and then we'll do this. So that means what I'm doing here is that this um, this fourth and this fifth item, these guys right here, are going to be correlated with each other within a dyad. So 34 and 35 are going to be correlated within women, and 34 and 35 are going to be correlated within men. And I'm also going to have 35 correlated with 35 across men and women. That's just basic. We do that whenever we have dyadic latent variables anyway. Same thing with 34. But now I've added a covariance where 34 in men, this item right here is going to be correlated with this item, number 35, in women. All right. And so we could kind of view that as this is kind of like a different form of dyadic coping. We can conceptualize it as, avoidance strategies, or it could be about, physical intimacy, or it could be all of these other ways in which we can kind of understand dyadic coping, but it isn't really kind of connected in a close way to the way we are actually trying to conceptualize dyadic coping. So one of the ways is to do this, and we'll again re-estimate the model. Technically, we'd want to do a likelihood ratio test, a chi-square difference test. But again, we can just kind of eyeball it. Went down even more. Our CFI and our TLI, they continue to get a little bit bigger. We'll scroll down to our loadings. Everything is looking okay. In terms of male and female loadings, there hasn't been a whole lot of movement. There's been a little bit, but All in all, not too much. And then we'll scroll down to our residual matrix to see kind of what's going on down there in terms of our problematic items. And as you can see here, these items are still causing a lot of problems. Right? So even when we're correlating them with each other, it's still resulting kind of in an overestimation of the covariance. And so from doing this, we could again continue to kind of plug away in trying to figure out what's going on. But it seems like again, these are two different kind of conceptual aspects of dyadic coping. So at this point, I would actually drop these items. All right. And so, some people are going to say, don't drop the items. Um, and so that could be, there's some potential argument for that, but also especially because you're using a validated scale, but also it just looking at it, even though I didn't create it, even though this limits my ability to compare this study to other studies that use this common this subscale, what it is going to allow me to do is actually to increase my construct validity. So because I'm really getting at dyadic coping in relation to like dyadic communication. And that's really what's paramount to me. All right. And I would just make a theoretically justified argument and I would walk the reader through all of these processes in my manuscript. All right. So I'll just go ahead and I'm going to kind of drop all of those two items from the dyadic coping inventory, those items 34 and 35, getting rid of these guys right here, and just focusing really on these first three items. All right. So oops, I oh, there it is. Gotta get rid of those two. All right, we'll scroll down. And so actually, I think, they're, oops, I, I thought I got rid of them both. I did not. All right. So now after dropping those two items, uh, our number of degrees of freedom goes down, but look at our chi-square, look at our p-value, even though it's not above 0.05 like we would prefer and would like it to be, my Lord, is it a whole lot better than where we were. Our CFI and our TLI are looking really, really good. Our RMSEA is really strong. The 90% CI is below, the one of the well respected and well known and commonly used cutoffs of 0.06. So this is telling me that we are increasing construct validity and we're really getting at that communication piece of dyadic coping. So we'll take a look at the loadings just to be sure that kind of everything's operating as it should be. And we see that this loading went down a little bit. This was around 0.70 last time. But again, this would be, again, still really quite substantial and meaningful. We have some really good loadings here, 0.77, 0.73, 0.81, or 0.80. And so to me, this would be kind of I feel comfortable moving on to the next step and beginning to interpret our actor and our partner effects. So given that, we'll kind of scroll up. And technically, you want to look at your unstandardized results because once you put things on a Z-score, you're going to be Z-scoring it for men and Z-scoring it for women. And even though we are using an item that is invariant, and those variances of the latent variables are going to be roughly the same, they're going to be really, really close to one another, as you can see. Technically, by z-scoring it, you're going to be dividing by kind of two different numbers. You're going to be dividing by the square root of this and the square root of this. And that might actually potentially bias your test statistics, your regression coefficients. So technically, you should use the unstandardized results. But again, if you have non-invariant loadings, unless you're in a p equals 0.049 versus p equals 0.051 kind of land, it's not going to have much of an impact at all. It's not going to be all that meaningful. And so in a manuscript, I actually report both standardized and unstandardized to satisfy people in both camps who want true comparisons with unstandardized versus effects on a metric that is meaningful to us, standard deviation units. All right, so we can kind of move past the measurement part of the model, and we can look at the actor and the partner effects. And so what we have here is we have relationship quality of men is predicted by men's reports of dyadic coping and women's reports of dyadic coping, right? And the effects are actually just about the same. There's not going to be much difference there. So the higher men are in dyadic coping, the more satisfied they are. The higher women are in dyadic coping, the more satisfied the man is. So that's going to be your partner effect. So this is your actor right here. You can just kind of match the subscripts, and or not subscripts, the kind of the labels I tacked on to the end. And if they have the same, they're going to be an actor. But if they're different, like we have here, then it's going to be a partner, right? For women, we get kind of a different pattern. We have male dyadic coping did not predict female relationship satisfaction above and beyond women's own reports of dyadic coping, right? And so again, that's a really quite interesting finding that there's kind of a different pattern of results here. And we could actually analyze that. There's the K parameter, which Tom Lederman and Dave Kenny have talked a lot about, and then there's more kind of modern uses of it, as well as new parameters. And what that K does is it really it's kind of a categorical indicator to what type of pattern, what is the pattern of associations. And so for men, we'd have a couple-oriented pattern of association where the actor and partner effects are equal, right? So even though we're not testing that, I can say with quite a bit of confidence that these are not going to be significantly different from one another, which means that the ratio of partner to actor is going to be, at the couple level, it's going to be around 1, right? But for women, we have an actor-oriented pattern. And that means that there's a significant actor effect, but there's not a significant partner effect, right? So we have, again, different patterns for different genders, and that could be of really really of great substantive interest, right? But again, I'm not going to go through dyadic patterns in this video. I will do that in another video. So just eyeballing it, we have, again, the regression coefficient is 0.386, and then here it's 0.785. This is an exceptionally large regression coefficient. And it's actually very characteristic of data between, or the association between dyadic coping and relationship quality. But these look fairly different. In fact, this is about, actually, it's a little more than twice as large as this. And then this is about 10 times as large as this. So we might have some gender differences here. All right, so even though this might not have been kind of an a priori hypothesis that we have, if we see something like this, this is where we'd run a post hoc analysis. So we'll kind of cancel out of that. And let's constrain the actor effects to be equal and just see what happens. And this will give us a 1 degree of freedom likelihood ratio test. All right. And so we can do that by just adding these labels at the end. And you don't need a space, but you can have a space. And what this will do is any parameter with this A1 at the end, that will be constrained to be equal to every other parameter that also has that A1 label. All right. So we can go ahead and we can run that. Right? And we can see that our model significantly decreased in fit. Before it was around, I believe, 87. Now it's above 91. And the critical value for a 1 degree of freedom likelihood ratio test is 3.84, which comes from the central chi-square distribution. All right. So we can scroll down, and here's where we can double check our syntax. All right, so 791, 791. All right, and so we can just see before this was 0.389 or 386, and now it's near 0.8. We can just, again, logically think that constraining this to be equal isn't really helpful, isn't an accurate depiction of what's going on, and it significantly harms the model, which means we have moderation here. We have the effect of dyadic coping on relationship quality is moderated by gender. So this is what's called a within dyad effect, a within dyad interaction, where gender moderates this pathway, right? This actor effect. Right, so that's something that, again, that could be of substantive interest, that the effect of dyadic coping differentially impacts relationship quality in men and women. Their own, I should say, their own reports of relationship quality. So now what we can do is we'll go ahead and we'll get rid of these labels. And I'm actually gonna, again, run it again just to get that chi-square in my head so I can do a rough guesstimate. So it's 87 and a half. And now we're going to constrain those partner effects to be equal. And you can make these labels really whatever you want. So generally I'll do PA1 or P1 for partner. And you saw I did A1 before for actor. So now we're going to constrain those to be equal, and we're going to do another, again, chi-square difference test. Again, do not do it in your head like I'm doing it. I'm just doing that for the sake of not making this video any longer than it already is. But we had was 87 and a half, and now it's 93, just under 93 and a half. So our chi-square difference is like 5.75, somewhere in there, which is well above the cutoff or that threshold of 3.84, which means we also have within dyad moderation of the partner effects. All right. And again, we can look at our effects just to be sure these should be identical. In the unstandardized, you'll see in the standardized, they're going to be slightly different. All right. So it's 166 and 173. And again, that's due to, again, men and women having slightly different variances on these items. And that's going to, again, have ripple effects. So that, again, that's why if you want to do true comparisons, you use unstandardized. But essentially what this means is that that the partner effect that women have on men is significantly larger than the partner effect that men have on women. And so this is kind of a no-duh moment for us because there is such a large difference. But oftentimes we might see an effect where the partner effect is 0.20 for men and 0.10 for women. Excuse me. And we want to see whether or not that's significantly different. So here it's a kind of an obvious example, and I've done that kind of intentionally to really emphasize, this within dyad moderation concept. But also we can test this on any actor and partner effect that we want, and sometimes it's going to be less obvious. One thing to consider when running these tests is statistical power. Oftentimes, in this example, it's not really a problem, but oftentimes, again, in that example, 0.20 and 0.10, you need to have the statistical power to detect that 0.10 difference in your regression coefficients. And oftentimes our studies are going to be underpowered. They might be powered to detect an actor in a partner effect, but they will be underpowered in order to determine whether or not there's within dyad moderation, right? Something else I will just briefly comment on that I've talked about in other videos is that essentially this is kind of a version of the ISAT model. In the ISAT model, you're constraining all parameters to be equal across gender, whereas here we're only doing it for the actor and the partner effects in separate analyses. Everything else is still free to vary. So if you're thinking to yourself, man, this is kind of similar to the ISAT model, you're exactly right. We're just looking at very specific parameters in terms of gender-based moderation. And so again, because this effect was significant, we want to remove this constraint from the model. So now I'm comfortable with this measurement model. So essentially what this is this is what's called the excuse me, the measurement model, where we aren't really kind of substantively interested in the effects as of yet, because we're just looking at our IVs and our DVs. And technically, you probably have with statements if you want to make it a true measurement model. But the idea is that we don't have any covariates in there. So now what we can actually do is begin to introduce the idea of covariates. All right, so we will throw in relationship length. All right, so this is going to be a between dyad variable because men and women have been in the relationship the same amount of time. And so they should theoretically have the exact same values. They don't often agree on relationship length. The correlation's only around 0.90, which means men say we've been together 31 years and women say it's 32. So it's not uncommon to have those differences, but theoretically speaking, they entered into the relationship at the exact same time. So we'll use that as a potential predictor. So what we're going to do in integrating that is I actually create a separate section. I do covariates. And what we'll do is we'll put our relationship length variable there. We'll have CSI for men, and we'll have CSI for women. We'll have our on statements, and then we will enter a semicolon. Technically, you do not need to enter a with statement because Mplus by default will covary all of your exogenous variables. So technically, we don't need to do this. All right. But I always do this just so I know what specifically is going on in the model, because sometimes I might forget that those variables are correlated with one another. And so this can actually be a problem if you get like a non-converged solution, because Mplus won't actually print the output for this. Whoops, that should be a with statement unless you actually type in the syntax. It will estimate it. It will account for that in the degrees of freedom in the model data fit, but it's just not going to report the output to you. And so because dyadic coping is so highly correlated, when you run into multicollinearity issues, one of the indicators is that there's an extremely high correlation between your IVs. And that's not something you would necessarily see if you didn't actually hard code this into the model and you couldn't see the output. All right. So again, I'm always a fan of typing in and coding everything that is going on with my model and making as few assumptions as possible. All right. So we can save that and we can run that. And then we'll take a gander at model data fit. We'll take a look at CFI and TLI, look at RMSEA. So it's all still good. It looks like it inserted some error in the model. This went up, I'd say, somewhat substantially, which means that there is going to be an effect of relationship length on the individual items. All right, because the structural portion of the model, all of our actor effects, all of our partner effects, and all of our covariances between our IVs and our DVs, as well as the covariance of our covariates with the IVs and prediction of the DVs, that part of the model is saturated, which means there's no degrees of freedom in that part of the model. And so that means you can't, every possible covariance and regression coefficient that can be estimated is being estimated. So if there's misfit that's happening, it's happening at the measurement level. And what that means is that this has a residual covariance with one or more of the items, whether it's the four CSI items right here or the three dyadic coping items. And that's where the misfit is happening. And sometimes that can be, kind of a nuisance and it's not really all that important. Or other times it can actually be really, really impactful. For those of you who are who have dove in more deeply into factor analysis, this is what's called differential item functioning, right? And I'm kind of presuming that here, just based on the model data fit, but we could always, again, take a look at our residual matrix to see if is there something that's kind of going on that is substantial enough that might warrant kind of investigation. And you see here, we got one that's a little overestimated. The association here between these two is a little overestimated. Um, Everywhere else, and here it's overestimated. Um, so here we kind of we might have a little bit of a problem. Doesn't seem to be, you know, extreme, but it seems like there might be a little something kind of going on there. And so actually I didn't mean to do that. I'll look at the kind of the significance. And so we have right here. These are exceptionally small effects. So there's one thing you could do is kind of drop them from the model. And I think that would probably be actually probably my first step is to drop a relationship length from the model and add in my other covariates one by one, kind of obtain my final kind of model, and then I'll actually add in relationship length back in at the end to see if there's any substantively different changes that are occurring. So that's one model building strategy. Another is that I think people actually, most people, most of the time gloss over. And by most people, I mean 98 or 99% of the people gloss over is maybe there's an untested interaction here where the effect of relationship length on CSI, couple satisfaction index, is moderating the effect, or I should say, is the effect is amplified by dyadic coping, right? So if we just think about this conceptually, is the way you engage in kind of stress communication with your partner, does it differ early on in your relationship from 2 years in to 10 years in to 15 years in? And the answer probably is yes, right? So in the first 6 months, you might even avoid conflict because you're still in that honeymoon phase. You don't want to rock the boat. But when you've been together 15, 20 years and you know each other's norms and you know the effects of when problems kind of fester and they're not addressed, you immediately want to engage in dyadic coping. So you could absolutely make the conceptual argument that there might be a difference here um, um, in the relationship between dyadic coping and CSI, and it's a function of relationship length. So I'm not going to go into kind of how you would test that. You just create an interaction term, and you'd most likely want to center dyadic coping and relationship length and test that interaction. But again, that's for another video on another day. But this is one of the things that you would probably want to think about. That would kind of indicate or presume that the model data fit problems that are induced by adding in relationship length is partially due to that missing interaction term, right? So those are some general ways of kind of addressing problems that you'll see in latent variable actor partner interdependence model, and you will see these issues kind of come up early, and you will see them come up often. So that is why I kind of took the time to kind of walk you through some of the measurement things that might be happening, some of the model data misfit things that are happening, because when you have all of these items in a single model, there's always the potential for there to be kind of residual covariances or underestimation, overestimation, model data misfits, and things like that. As you get more and more degrees of freedom in your model, the more and more that's going to happen, and the more and more you need to pay attention to those types of things. So hopefully this has been helpful in learning how to both code the latent variable actor partner interdependence model, but also addressing a couple, not again, the exclusive list, but a couple of the issues that you may encounter along the way. Thanks so much for watching.